Hey everyone, and welcome back to Ideanthro. Now, you can obviously see that we're using a little bit of a different format today in that we're using the screen capture software to show you some stuff on the computer. Now, the reason for that is because of what we want to show you today. So in some of our earlier episodes, episode 2 about precinct scale systems and 3 about large bioretention systems and so on, we talked to you about different types of bioretention system and the way that you can distinguish between them and how that's useful when it comes to talking about them and discussing them in terms of design and maintenance and so on. Well, we're continuing with that general theme today, but we're going to show you another way to break systems out, and that's by what's going on underneath the ground. Because there's a whole bunch of different ways you can arrange the stuff underneath the ground in a bioretention system, and it's really useful. So we wanted to show you that, but of course we can't see what's going on underneath the ground if we just go out on site. You can get a few hints though, right? There's some stuff that you can look for, but you can't get a really good idea of it. So we're going to be referring to some guidelines published by other organizations, but they're really useful documents and they're super cool for this purpose. So we're going to refer to those, and they're freely available, so you can get them and you can use them in your work. So we want to refer to those. When someone's got really good stuff out there, let's refer to it. So, do we need to touch off on anything else before we continue? No, we're probably all good. So, let's show you the two documents. So the first document that we're going to talk about today is one published by Healthy Waterways. This is the main one we'll refer to. I'll show you where to get it. So Healthy Waterways website, healthywaterways.org. Go to Resources, go to Water by Design. Then we just scroll down a little here until we get to the Bioretention Technical Design Guidelines. And we're talking about the October 2014 edition. There was an earlier one from 2012, but this, at the time that I'm recording this, is the most up-to-date version. So that's the first one. I'll show you one other really good document in a sec as well, but this is one we're going to refer to mostly. So this document is published by Healthy Waterways, which is a South East Queensland based organisation in Australia. The document's primarily written for Queensland conditions, but as with most things bioretention, you can pick up, like most of the stuff is transferable from region to region. The vast majority of it is equally applicable no matter where you are, right? So if you're not in South East Queensland, don't worry about this. You know, what we're talking about today, there's heaps in it for you. The other document that you should be aware of, particularly if you're in Australia, is one published by the CRC for water sensitive cities. So we can go to their website, which is watersensitivecities.org.au. You can hover over publications, scroll down to technical reports and fact sheets, and click on that. And if we scroll down just a bit here, we will find their adoption guidelines for stormwater biofiltration systems. That's also another really good guideline. If you want to know more about bioretention systems and you want to read about it or you want to go into more detail or that sort of thing, that's a really useful document. But today, we're talking about the Healthy Waterways document, and conveniently, I have a copy open right here. So, this is what the document looks like. If we start flicking through it a little, you go through first section, tables, all that stuff. Introduction is kind of about the document itself. Section 2 is where things get a little bit more interesting. So it starts off with a bit of a description about what bioretention systems are, what the different parts of it are, and then we get into these few pages that talk about different types. Very similar concept really to what we did in some of our earlier episodes. They break it down a little bit differently, but that's cool. There's some nice pictures and the like. We flick through, but then coming up soon, we get to this bit, section 2.4, drainage profiles, and this is what we're talking about today, right? So in here, we go to the next page, so this is page 28 of the document. We have these 4 different drainage profiles for bioretention systems. We'll zoom in a little and look at those types here. So type 1 is something called a saturated zone system, type 2 is a sealed system. We'll scroll down here, type 3 is something called a conventional system, and finally type 4 is something called a pipeless system. We're going to look at each of these in turn. So, and this is useful because they've all got different uses. So if you're coming from this design point of view, they all have different strengths and weaknesses. And if you're coming out from a maintenance point of view, while the maintenance will be 95% similar across all of them, it's good to know the differences you've got because there might be a few different things that you look for, right? If you had a system that was blocked up and it's, say, a conventional system which definitely has an under drainage pipe, well, you might want to be checking out what's up with that pipe, perhaps. It's not the only reason a system could block, but you'd want to be aware of that. But if you know that you're looking at a pipeless system, you don't have to go there, right? different things going on, different maintenance responses. So we're going to look at these three different types. We're going to start with type 3, conventional, because as the name suggests, this is probably the type that is closest to what was originally envisaged when people first started talking about bioretention systems. And of course, like everything, it's adapted and changed over time, but this is probably closest to what was envisaged in the early days of this stuff. Before I go any further, I should point out though, there are 4 types here, and we're going to talk about 4 types. This isn't the only ways that was amazing grammar, Jack. These aren't the only ways you could describe bioretention systems. There are a number of different ways you can arrange the stuff that's going on underneath the ground, but these are the 4 in this guideline. There are 4 that are used relatively commonly, and so on. But there are other ways, and if you think you've got something that works better for your site, think it through, use your common sense, all of that stuff, and you might well be right. But anyway, type 3 systems. This is the one that was probably closest to what was originally envisaged. And what we see here, so if we start at the top of the system, obviously we have the plants. There'd be a layer of mulch on the surface. There'd be the filter media, like in all bioretention systems, which is what the plants grow in and what helps with a lot of the pollutant removal and that sort of thing. We have a transition layer, which is a coarse sand. This stops the filter media falling down any further in the system. We have a layer of gravel, and that surrounds the under drainage pipes, which are very often made from PVC with slots in it, but occasionally they're made from ag pipe, so the flexible black pipe with holes in it for drainage. And the other distinguishing factor in this system here is the fact that the base of the system does not have an impermeable liner. It could have a permeable liner to distinguish the base of the system from the in situ soils, which you see there, but it doesn't have an impermeable liner. That means that water, as you can see here, can drain out the base of the system as well as out the under drainage pipes. So this is the sort of system, this is a really good sort of system to use, because one of the problems with urban development is we go from a natural catchment where there's lots of trees and lots of vegetation, and it rains. If it rains a small bit, the water just gets caught in the leaves of the trees and evaporates and doesn't make it to the ground. But if you get a bigger rainfall event, not a massive one, but a bigger one, the water makes its way to the ground, and because the ground is permeable, it all soaks into the ground. So you get lots of water infiltrating, right? And if it's a massive storm event, eventually you can fill up the water stores in the ground or have it raining so quickly that you get surface runoff. But an awful lot of the water infiltrates into the ground. Urban development, on the other hand, we place heaps and heaps of concrete, roofs, all these impermeable surfaces over the ground. So the water doesn't infiltrate in really regularly. And we get heaps more runoff. The quantity of runoff is heaps bigger. And then, because of that, we get more erosion in creeks. As all that water erodes our creeks, it takes more pollution to the creeks and so on. So it's, in general terms, in most instances, obviously it's site specific, but in general terms, it's a good idea to try and infiltrate water from the base of your bioretention system into the ground beneath. And so if you've got a site where the soil is reasonably permeable in your bioretention system, maybe not pure sand, because if you're on pure sand, as I'll talk to you about in a minute, you'd go and look at one of these pipeless systems over here, right? But if you're on reasonably well draining soil, not well enough that we don't need an under drainage pipe in it, but reasonably well draining soil, and that soil's not dispersive or this sort of thing, where infiltrating large amounts of water into it would be a problem, then in general terms, it's a good idea to infiltrate water into the surrounding soil. So we have an impermeable base on the system. So that means the first bit of the water that comes down can just get to the base and infiltrate in. Now, if it's a big rainfall event, then we might get water starting to back up in the system, and you've still got this under drainage pipe there to convey the water away. But yeah, you've got this infiltration going on, which is generally good. I should note at this point that I'm talking fairly general terms here, and this guideline provides a little bit more detailed information about exactly how to pick which system. So I'll just show you that. So we'll zoom, wrong key, Jack. We'll zoom out, and if we flip forward here, I believe the page is page 39. Sorry, page 39, figure 16 is this lovely flow chart here that will help you pick which type of system is best for your site. So just be aware of that. I'm talking in general terms. I might not cover off on absolutely everything. You should probably be referring to this flowchart and of course using your common sense when you're doing this. Anyway, back up to our sketches here. So that was the conventional type of system. If we zoom back in, we'll now take a look at the type 2 sealed system. So if we look at this, again coming down from the top, we've got the plants, we've got the mulch, we've got the filter media, got the transition layer, and then we come to the gravel, the under drainage pipe, but this time we have an impermeable liner here. I know it just says liner, but the point here is this is impermeable, which seals off the base. So that liner is impermeable along the bottom of the system, but it also would extend some distance up the sides. Exactly how far might depend on the particular use, and I know you can't see it in this diagram, but it would extend some distance up the side of the system, depending on your exact use. So this would particularly get used if you had, say, dispersive soils. So dispersive soils being where any water that comes in contact with the soil, it's got these fine clay particles that that erode really, really easily, come into suspension really easily, and it causes heaps of erosion, right? So obviously, if you're building a bioretention system on that, you probably don't want to be infiltrating large amounts of water into it because you'll just end up completely eroding out underneath your system and structural collapse and a whole bunch of problems, right? So in that case, you might put an impermeable liner on it and you're looking at a type 2 sealed system. Obviously not quite as good for the hydrology benefits that we talked about with the type 3 system, but still obviously doing all its treatment up in the filter media and this sort of stuff, and it's got the under drainage pipe to get the flows away. So a totally functional system. We also see these used quite commonly as a fallback option, right? So a really small site, doesn't have a budget to do heaps and heaps of geotech, not 100% sure what's underneath the ground, what's a safe option? Oh, type 2 sealed is more conservative than the type 3 conventional, so people do go that way. Yeah, obviously I'd prefer that people were able to do the geotech and put in exactly the right system in the right instance, but people do fall back onto this as a conservative option from time to time. Now here we'll skip down and go to the type 4 system. So as I mentioned with the type 3, it's good to infiltrate water into the ground. And in some circumstances, your ground might have so much capacity to infiltrate water that you don't actually need the under drainage pipe that you see on the type 3 system at all. And this is typically if you're, at least in southeast Queensland, the only spot that this occurs is if you're right down near the beach. Right, so you're on sandy soils, like pure sand soils, and to make the system, you've dug a hole, you filled it up with the filter media, you've got your plants growing in it because that's a more hospitable and better treatment environment going on in that filter media rather than just the beach sand. But underneath, you've got sand, essentially, right? So in that instance, a pipe 4 system is cheaper to build because you don't have to put in the pipes at the base. You don't also have to have some sort of outlet pit, which I know you can't see in this diagram, but like a big concrete pit for the pipes to connect into. It's a much simpler sort of system. So it's a cheaper, lower tech sort of setup. So if you've got the sandy soils and that sort of thing, it can be a really good option. This in many respects for any viewers in Western Australia, I know that not all of Western Australia is on sandy soil, but I certainly know that parts of the Perth area are. This could be an option there. Of course, what you're noting is that bioretention systems, they're great for stormwater treatment, but they don't remove all the pollution. So in this instance, that pollution is the pollution that's not removed, the residual stuff, is then going into the subsoil and possibly into shallow groundwater. Whereas of course in the type 3 conventional system or the other systems, the unremoved pollution would go to surface water because the under drainage pipes will connect back to the surface water. Just a distinction to be aware of there. And the final other type of system that we're going to look at today is what's referred to here as type 1 saturated zone system. So a saturated zone system incorporates a water store at the base of the system. So if we work down from the top, we have the plants, we have the mulch, we have the filter media. Then below that, things start getting a little bit different. The first difference we'll see here is that the depth of the sandy transition layer is a lot thicker, right? So we can see in the type 2 sealed, we've got about 100 mils of transition layer. Over here we've got a much thicker layer of sand for the transition layer, and that varies depending on the design, and this document references us out to another section with some more detailed information. But going below that, then we get to the gravel, we get to the under drainage pipes, and there is an impermeable liner to seal the base of the system, because we've got a water store, right? So we need to seal the thing up so it retains water. Now, here's the thing. This particular diagram doesn't do a great job of showing exactly how this works. So I'm actually going to skip forward to, I believe it's page 79 in this document. Yep, here we go, which shows a few configurations of the outlet pit to describe what's going on. And we're going to focus in on this one over here, option 2. So we'll just zoom in a tiny bit more. There we go. So option 2, this one over here. So coming down from the surface, plants, mulch, filter media, thicker transition layer than you'd expect, drainage layer made out of gravel, under drainage pipe. And then what you see here is the under drainage pipe comes out, and this is the concrete pit. Here, this is the pipe to take the water away at the very end. And we've got this riser arrangement here. So the pipe comes out, it extends horizontally, but there's a screw cap on here that blocks it. There's this T-piece where water can come up and come out over the top of the system like so. And what this means is that the top of this pipe here sets the water level that gets stored back in the filter media here. So you can imagine this thing has just been built. It's never had any water before, hasn't rained before, anything like that. Rain event happens, water trickles through the media, starts to fill up through here, gets into the pipe, nowhere to go. So it backs up. More water comes in, backs up, backs up, backs up. It's backing up both in here and over in the pipe over here. And it backs up until the point where it can finally tip out over the top, like so. And at the end of the rain event, water drains down, and it drains back till there's just, this store left in the base. So you've got this store of water, and that's beneficial for a few reasons. There's been a bunch of research done on the effects of pollutant removal on this, and it does have some effects. We won't go into that now. It's got some pros and it's got some cons here. But one really cool thing that it does, and this will explain part of the arrangement here, is that by having this storage of water at the base, it allows wicking to happen to draw moisture up into the filter media and make more moisture available to the plants. And that helps to keep them healthier for longer. And that's particularly important if you're building a bioretention system in a climate with a long dry period. So from my point of view, I'm in southeast Queensland, but if you went up further north up the coast to somewhere like Townsville's, in the tropics, in the dry tropics, but it's very wet in summer for 1 or 2, maybe 3 months a year. Then they have a really long dry period with virtually no rain. And we know from experience that if you are using, say, a type 3 system, your plants might struggle a bit over that time. But the saturated zone system, that can help by leaving a bit of a water store to wick water up for just a little bit longer. It won't last the whole dry season, right? But it will make the plants, we'll give them just a little bit more buffer, a little bit more resilience, and so on. So the other thing to note here is you'll notice we mentioned this thicker transition layer. So there are a few different arrangements. You can't just whack a riser and an upstand onto a standard bioretention system here. So imagine this didn't have this thick transition layer and just had standard filter media, standard thin transition layer, standard thin drainage layer, right? You stuck the riser on there and suddenly the water level would back up into the filter media because the filter media would come down lower, right? Back up into the filter media. That's a problem for pollutant removal. This saturated environment that we're creating here can cause phosphorus to leach from the base of systems. I won't go into why that's the case, but it can cause that to happen. And so the filter media is there to remove phosphorus from the system, but if you saturate it permanently, you can free up the phosphorus from the filter media and cause some leaching. And that's one of the reasons why we have this thicker transition layer. So we make the transition layer that's coarse sand, doesn't have any phosphorus in it, we make it thicker so that the water level sits within the transition layer and within the gravel, like so. And that way, we don't risk the phosphorus leaching. Now I can hear you thinking, well, why did you make the transition layer so thick? Why not just make the gravel really thick, have a really thin transition layer, and then filter media? Good question. That was actually the original way a lot of these systems were designed, when they were primarily looking for pollutant removal benefits, and particularly for nitrogen removal benefits. They were trying to make this water store to help with denitrification, a whole bunch of other stuff. And those early systems, at least in an Australian context, had a large gravel layer. The problem with that is that the gravel layer is really thick, and that the top of the saturated zone is in the gravel. Gravel has really big particles relative to the filter media, or the sand, and those particles have big gaps between them. So you can't get any capillary rise, so you can't draw moisture up into the filter media. And hence, a system with a really thick gravel layer isn't as good for sustaining plants because you can't get that capillary rise. But the coarse sand, it's better. Maybe not perfect. The filter media itself will have better capillary rise than the coarse sand, but it's sure as heck better than the gravel, right? So hence why thick transition layer. So let's just go back to this first page we looked at here, and I've forgotten the page number, so never mind. We'll zoom back out. We'll go all the way back up. Went a little bit too far. I apologize for that. That's right. It was page 28. So back here we are. The 4 types we were looking at earlier. Yeah. So that's it for this episode. As I said, it's important to know about these different types of, the drainage profile, what's going on underneath the soil, underneath the surface in these systems, because it'll definitely affect design, because I've talked to different types of systems are more applicable in some regions than others, some situations than others, and so on and so forth. So it's really important for design, but it's also important for maintenance, because there could be a few nuances in how you maintain each type of system. Majority of it's going to be the same, right? So you shouldn't be freaking out that this is a massive extra extra workload or heaps of extra stuff to think about. It's 95% the same between a saturated zone system and a sealed system and so on, but you should still be aware of it. So final comments I wanted to make on this are, obviously, respect the fact that there are some nuances in where you should use each system, and use your common sense and refer to guidance like the relevant table in this document, which is the relevant figure in this document, which is figure 16. Respect that, use your common sense when designing them to get the right system in the right place. And I would like to say thank you to Healthy Waterways for publishing this document, freely available. It's great that people are out there sharing guidance, sharing these sorts of resources that allow us all to learn and to then apply the best knowledge and the best technology in the best spaces. So I appreciate that document's freely available, so that I can then show you guys this and talk you through this sort of thing. And also then thank you to the CRC for Water Sensitive Cities for their design guideline that we had a look at before. And that's probably it for this episode. So thank you for tuning in to this episode of Ideanthro. If you'd like to know more about what we do and that sort of thing, our projects, our episodes, all of that stuff, you can go to www.ideanthro.com. You can find everything there. You can also find us on Facebook, where we post regular updates. You can like the page to keep up to date with stuff. That is facebook.com/Ideanthro. And you can find us on YouTube, where we post all our videos. Cool. Thank you very much for tuning in. I hope you found this episode interesting. And until next time, have a great time. See ya.